Hey guys, hope you're doing well. Most of you have seen the Serenity Prayer, no doubt. It's very popular in Christian art. God, grant me the serenity to accept the things I cannot change, courage to change the things I can, and wisdom to know the difference. This is the part of the prayer that's on like wall hangings, and rightly so. Probably right now there are many things that we cannot change. There's more to the prayer, and I really like it. Living one day at a time, enjoying one moment at a time, accepting hardships as the pathway to peace, taking, as he, Jesus, did, this sinful world as it is, not as I would have it, trusting that he will make all things right if I surrender to his will, so that I may be reasonably happy in this life and supremely happy with him forever and ever in the next. This lesson is about sections 3.5, lesson 3.5. There's a note packet and an associated Excel spreadsheet on Brightspace. The note packet looks like this. It's going to use the example data in the Excel file, which looks like this. It has a number of different cars. Here are the models. Here are the weights of these cars in pounds, the sizes of their engine in liters, and their gas mileage as tested on a city track by the EPA, who is the agency responsible for doing such things. And what I would like to do is predict the mileage of a 3,000 pound car whose engine size is 3.5 liters. Well, this is a regression problem, or can be approached by regression. So I could run linear regression and use mileage as my dependent variable, weight as my independent variable, and get a regression equation. Or I could use engine size as my independent variable, mileage, of course, still my dependent variable, and I'd get a different regression equation. And then somebody reasonably bright said, why do I have to choose between the two independent variables? I know both the weight and the engine size. Why can't I use both? And if I do, shouldn't I expect to be able to get a more accurate prediction? So the answer is yes, you can use both, and you might get a more accurate prediction. The goal is still the same. Here's the actual data value or mileage minus its prediction. Take the difference of those and get our error or residual square, add those together, sum of the squares of the residuals. Try to minimize that. But the form of the model is what's different. Instead of having a bunch of data points in two-dimensional space with independent variable and dependent variable, and then trying to fit a line near those data points, now we have a bunch of points in three-dimensional space. One independent variable, weight, another independent variable, engine size, and the dependent variable, mileage. And now we're not trying to fit a line through the points, we're trying to fit a plane, which is a flat two-dimensional surface through or near these points. So the form of our model is going to be mileage equals some number plus a coefficient times the weight variable plus another coefficient times the engine size variable. And these beta 1 and beta 2 coefficients can be thought of as slopes. A plane has two slopes, one with relationship to one of the independent variables and the other how steep it is with respect to the other independent variable. Okay, we're going to have to give up on the geometry, and Excel doesn't have a graphical feature to do problems like this anyway, nor do we want to restrict ourselves to two independent variables. We could also add a third independent variable, say drag coefficient, a measure of the wind resistance of the car. So we're going to leave the geometry behind and put ourselves in the hands of the algebra. So let's attempt to get a model for mileage as a function of both engine size and weight. We'll need a package in the data analysis package. We'll need a command in the data analysis package. So in case it's been a while since we used that, in case you've forgotten and don't have it on your taskbar, if you go to File, Options, Add-ins, and Go, and then make sure that the analysis tool pack is checked. So that's how it works on a PC. If you have a Mac, Google, Data Analysis, Excel, Mac, or something like that. So once you have the data analysis command, let's run it and choose the command regression. Click OK, and it brings up a dialog box like this. So first it wants the Y range, which is the dependent variable. Remember, that's mileage for us. And so I'll drag down through that column. Then it wants the X range, or independent variable. Now we have two independent variables. So it's critical that they be, for Excel, that they be side by side in adjacent columns like this. If not, I'll move them or copy columns, insert columns, whatever it takes to get the independent variables side by side. And then I can drag not only down that column, but across two columns like this. As far as the rest of the dialog box, let's check labels, since we did highlight those in the when I did my highlighting. Don't need to change anything else up here. And I probably would leave this new worksheet apply or tab. And so we're ready to go. When you click OK, Excel gives you back a whole screen full of information in a new tab. My original data is back here. Now I'm in sheet 2 that Excel just created, and it has the information that's printed on your worksheet. So the things that I want from the Excel printout here, first of all, most of the good stuff is right here. And you should always include labels when you highlight your data so that Excel will let you know what's what here. So Excel is telling me now that mileage equals, and the first thing, the intercept, is that beta 0 coefficient we were talking about, 41.47. Then there's the coefficient that goes on the weight variable, minus 0.0053 times weight. And then the coefficient times the engine size, minus 0.95 times engine size. So that's our plane that best fits these data points. And now we have three choices of model, actually. One would be to just use the weight. Another would be to just use the size. And the third option we just generated, to use both weight and size. So now I want to pick between these three models. Here's a technical fact. It turns out when you do multiple linear regression like this, that adding more independent variables tends to increase the R squared, even though in real life it may not be giving you much better results. And so statisticians usually adjust it in a complicated but looking, but really it's just arithmetic here, to be able to correct for that fact. The only thing to be aware of here is that the adjusted R squared can actually turn out to be a slightly negative number, but you don't need to worry about that. Here are the three regression equations. So here again were our options: number 1 to use just weight, number 2 to just use engine size, number 3 to use both. Here are the three regression equations. And now to compare the accuracy of these models, I want to come back to the output screen And right here is the adjusted R squared. So I have taken that value and copied it here. And though I won't go through it, I also ran regression just with each of these independent variables, got the regression equation and the adjusted R squared as well. So now it's decision time. First of all, which of these three combinations of variables is best? Well, depends what you mean by best. So clear back at the beginning of the course long ago, we talked about some criteria that could be used to evaluate models. One was simplicity. So which is the simplest model? Well, definitely not number 3. It has 2 independent variables. So that would be between number 1 and number 2. And number 1, you can see, has a considerably higher adjusted R squared than number 2. So if I'm going for the simplest model, there's no question I should use just weight by itself. If I'm interested in all the accuracy that I could get, so most accurate, then just brute force comparing the adjusted R squared, number 3 does just a little bit better. So weight and size. Well, that still doesn't answer the question, which one's best? Well, it depends on, again, what criteria you're most interested in. In this case, my personal opinion is that the increased accuracy using weight and engine size above just using weight is so small that it's not worth the extra complexity. So probably most people would say, since weight alone is almost as good as both variables, almost as good as both variables, use just weight. One more thing. We talked in the last lesson about the fact that the R squared explains how much of the variation in the output can be explained by the variation in the input. So here are the adjusted R squareds. Just to be technically correct, I'm going back to the actual R squareds before they're adjusted. And it turns out that engine size will explain 62% of the variation in mileage, and weight will explain about 76% of the variation in mileage. Well, these two things together add up to more than 100%. And so how can that be that I can explain more than 100% of the variation? And the answer is that the real picture is like this. Let's draw a Venn diagram of the effect. So here's weight, and it can explain 76%. And then here is engine size. And it's a little smaller. It can explain 62%. But the point is that they have enormous overlap. I mean, think about this in real life. Which cars tend to have larger engines? Those that are bigger and heavier. So weight and engine size are not independent of each other. They have a strong relationship themselves. So just to note, we could say something like weight and engine size are correlated themselves. And that's important information to know as you correlated themselves. So size gives little new information. Little new information. That's important when modeling. You don't necessarily want to throw every possible independent variable that you can think of at a problem, because typically the independent variables are related and you're just adding layer after layer of extra complexity for not that much additional accuracy. We'll talk more about that in a future lesson, and we'll stop there. Thanks.